All right, let's continue with the second learning objective that is learning different ways that a limit can fail to exist. And I'm going to show this concept, failing limit concept, on an example here. And the function here is f of x equals absolute value of x divided by x, and the question is asking us to evaluate the limit of this function f as x approaches 0, and in fact we're going to show that this limit does not exist. All right, to show that the limit fails to exist, we can look at the definition of the absolute value function. So the absolute value function is defined as, for positive x's, including 0, the function takes the value of x, and for negative x's, the function takes the value of negative x. So that's the definition of the absolute value function. But we do have absolute value of x divided by x. So that means we're going to look at each piece here divided by x to get down to absolute value of x divided by x. So this function is still a piecewise function as the absolute value function. So the first piece here divided by x takes you to 1, and the second piece divided by x takes you to -1, but watch out that x equals 0 is a problem point. That's where we check the limit for, because this function becomes 0 over 0, which is undefined, right? So x equals 0 is not in the domain of this rational function here. In fact, x equals 0 is in the domain of absolute value of x, but we're not interested in just absolute value of x, but absolute value of x over x. So essentially, we had to remove this equality sign here from here to here, because the function, again, is not defined at x equals 0. So the good news here is that the function either takes the value of 1 or taking the value of -1. So for positive x's, it's going to be just a straight line, horizontal line, right? And for x is less than 0, it is just 0. So you can also look at the table of simple values, but that's not going to be hard for you to check, because as I said, on the right of x equals 0, the function takes the value of 1, no matter what x you go with, right? And on the left, it's -1. So essentially, from starting from here, if you walk all the way down and get closer to 0 for x, the function values approach 1. Okay, here we go. Even though there's a punch over there, we know that on the right, the function values approach 1. On the left, if you walk in this direction for x, then the corresponding function values get closer to -1. So on the left and right, you have different limit values. So that implies that we have a failing limit case for this problem at x equals 0. So here, if I choose a neighborhood of 0, like minus delta, the Greek letter delta, and plus delta, so here is our observation. So if delta is a positive number, then you have on this interval function values approach 1, and on this interval function values approach -1. So here the conclusion is that the left limit is different from the right limit, or f of x approaches approaches different numbers on the left or on the right of x equals 0. For that reason, here the conclusion is the limit does not exist. Sometimes we use the symbol here, d and e, just to say like limit of this function, absolute value of x over x as x approaches 0 is capital letter, all capital D and E, which stands for does not exist. All right, let's go over common types of behavior associated with non-existence of a limit. The very first case scenario is in fact the example I just went through. So f of x approaches a different number from the right side of C, then it approaches from the left side. That's a very common behavior, and we just did an example for that. And the second and third examples, I'm going to show a few animations on Desmos. So the first one that I'll go through here is f increasing or decreasing without a bound as x approaches c, and the last one I'm going to show you is that f of x oscillates between two fixed values as x approaches c. All right, here's the example for case number 2, that f of x increases or decreases without a bound as x approaches the limit point. So let's see what we have here. So we have f of x equals 1 over x. We can easily see that x equals 0 makes this function undefined, right? At x equals 0, f is undefined because we're dividing by 0. But we can still look at the limit of the function as x approaches 0. So now the question is like, what is this limit? All right, let me just show you what that is graphically. All right, here's the graph. So as you see that when you get closer to 0, the origin from the left and right, the corresponding values are diverging away. In fact, let me zoom out here. So it shoot like on the right of 0, the function values shoot all the way to infinity. And on the left, as you see, when you get closer and closer, let's see what happens. It shoots down all the way to negative infinity. Okay? So this kind of behavior shows us that the function values increase without a bound to infinity, or decrease without a bound, which means like the function approaches either infinity or minus infinity as you get closer and closer to 0, either from the left or from the right. So this is a very typical example of the case number 2. All right, for the case number 3, I have a very cool example. It's an example of a function oscillating between two fixed values as x approaches the limit point. So here we go. The example for that is f of x equals sine 1 over x. And very immediate observation is that at x equals 0, this function is not defined. At x equals 0, f is undefined, but we can still look at the limit of the function as x approaches 0. Okay. By the way, the answer of the previous question is just does not exist. We put like d and e essentially means that the limit doesn't exist. Now let's see what's going on with this function. If you want to graph this function, this is what it looks like around 0. All right, here's the graph of sine 1 over x. Sine, by the way, takes the values in between -1 and 1. We know it from trig. And as you see that this blue dot moves in between -1 and 1. In other words, it oscillates between -1 and 1. And as I get closer and closer, as you see that fluctuations are increasing. And this limit behavior tells us that the function values do not approach a certain value as x gets closer to 0, because it oscillates and oscillates and oscillates, so it doesn't converge or approach a function value. All right, the conclusion here is that this limit does not exist. All right. All right, that's all I have for the two learning objectives of this section. So please go over my recitation videos to practice all of these conceptual definitions, and I'll see you in another video. Bye.